2 now of our lecture about meteorological instruments. So we're going to start talking about ways of measuring the wind. The generic term for an instrument that measures the wind speed is an anemometer. Anemometers take in situ observations of wind speed. And your book talks about 4 types of anemometers that are all useful for different purposes: cup anemometers, sonic anemometers, hot wire anemometers, and Pitot tubes. And we'll spend some time on each of those here. Now, the one that you're probably most familiar with seeing is a cup anemometer. That's the thing that usually has those 3 little cups that are mounted on a pivot, and they're spinning up there. They are very cheap. You can find these things on, go to Google Shopping or Amazon or something. You can find these things for as little as like 20 bucks, or even probably less, or you can get a very high quality one for hundreds of dollars. But in the great scheme of what weather instruments cost, these are relatively cheap, and they are extremely reliable. They will continue to operate under surprisingly large range of temperature conditions, rain rate conditions, etc. The instrument itself does not require power. It is going to be, we'll talk about how they work in just a minute here, but the instrument itself doesn't require power. Now, if it's in a situation where you need to have like a heater on it to keep ice from accumulating on it, that might require power. But the instrument itself doesn't. And these kind of cup anemometers are by far the most common way of measuring wind speed in wind power applications. They are not by any means our most precise or most accurate way of measuring the winds, but they are cheap and reliable and get the observations accurate enough that they are usually what we use in a wind power application. The way they actually work is that spinning shaft. We talked about this once before, but the spinning of that shaft is used to drive a small generator inside of the housing there, and that generator produces a voltage. Depending on the voltage is something we have standard tools to be able to measure in electronics, and from that voltage we can figure out the rotation rate. So it's not terribly exotic in terms of how the thing works. It's basically just generating a little electrical potential, which we have tools that can measure. And so, well, if there's this much electrical potential, we must be spinning at this many hertz. Notice the unit there, hertz, as in how many times per second it is rotating. Now, the business of changing that rotation rate into a wind speed, that's a much trickier problem. If I have a top-down view here of a cup anemometer here, I actually downloaded this off of a patent application I found on Google. God, I love Google. So the thing is going to sit there and spin. Now, I drew some wind arrows there. When the wind blows, it's going to make the little cup anemometer spin. But what is the rate that the cup is going to spin compared to the speed of the wind? It isn't simply like the tangential speed of the wind as it goes, across the path of the cups. There's a lot of complications here as these cups are turning. See, part of their rotation rate is up. Part of how they rotate means that the cups are going upwind on one side. See, like on this case here, the half closest to the bottom of the screen, those cups as they're turning are actually going upwind. So you can't just assume like the top cup there is going with the speed of the wind, because it also is fighting the fact that it's turning the other cups upwind. So this is tricky. It's not really possible to come up with an analytic answer for a wind speed of 5 meters per second. The cups will be turning at a rate of this many hertz, this many rotation rates per second here. Rather, we have to calibrate the thing. And I have a YouTube video playing here that I found where they were calibrating a cup anemometer in a wind tunnel. In the wind tunnel, we know to high precision what the wind speed is, and so we can then put the anemometer in there under very controlled conditions and measure what is the rotation rate of the anemometer. And from that, we can, when we know the wind speed U, and we can measure the rotation rate S, and we can put that together on a scatter diagram here, where I have the rotation rate on the under a range of conditions under the on the x-axis, and the known value of the U of the wind U on the y-axis here. And we could actually see, oh, there's a nice relationship between the rotation rate of this particular anemometer and its wind speed. And we actually used fairly standard tools. I'm going to use the notation that was in your textbook here, where they kind of created a regression line here, where the slope of the regression line is that script L, and the y-intercept of that regression line is U naught. To be able then to describe, given any rotation rate S, we now know with this calibration of our anemometer, we now know what the wind speed is. I don't like this notation of script L for slope of the regression line and U naught for the y-intercept of the regression line. Survivors of Energy 301, the statistics class knows that there's much better ways to do that, but we'll stick with what the book is saying here. So once your anemometer has been through all of this kind of calibration there, any anemometer worth paying for your energy purposes is going to come with some kind of calibration certificate, which, by the way, I found out are really hard to find online because nobody wants you just to print your own calibration certificates, right? They need to come from an actual accredited institution that calibrates your meteorological instruments. Anyway, okay, so that is how we would be working with a cup anemometer and calibrating it and so on. And cup anemometers and the very closely related propeller anemometers, you know the ones I'm talking about, where they kind of have like the propeller of an airplane kind of thing on front of it, which works in very similar sort of ways. They're certainly sufficient for most wind power applications, but there are plenty of applications where you need better observations of the wind. Either you need them to be more precise or more accurate than a cup anemometer can provide, or you need the three-dimensional wind, not just the horizontal, but also the vertical components of the wind, in which case you're going to need to turn to something like a sonic anemometer. I have a picture of a sonic anemometer. That's not the greatest example of one right there, but I'll show you some better ones in a little bit. But sonic anemometers actually are able to measure both the wind speed and the wind direction. The cup anemometer was just measuring wind speed. Cup anemometers don't actually have that good of temporal resolution. They can't tell the difference between the winds of like 1 second to the next second very well. Averaged over like a 10-minute period, they're pretty good, but the temporal resolution of a cup anemometer is not great. On the other hand, sonic anemometers have extremely high temporal resolution. They can distinguish the winds up to like 20 times a second, which is actually essential for certain types of meteorological calculations. To compute things like the rate of turbulence in the atmosphere has to be measured at those kinds of timescales, or the rates of conduction of heat from the surface of the Earth into the atmosphere by turbulent processes, or the rate of evaporation off the surface. Those all require those kinds of measurements at those kind of scales. In the context of wind power, probably not. Another advantage of the sonic anemometers is they have no moving parts. There's just not anything there to break, to get crusted with salt, to get anything. But they do require a fair amount of power, and they are requiring a lot of maintenance. Now, but just by the name sonic anemometer, and I like this sonic anemometer that's mounted out on a boom a lot better than that first one I showed you. This, as just by the name you can guess, sonic anemometers use sound to measure the speed of the wind. And generally speaking, they are oriented so that they have 3 pairs of sensors. You can kind of see there's like a sensor on each end of those sort of little sticks that are out there on this one here. And they are oriented orthogonal to each other. There's a set of sticks that goes east-west, a set of sticks that's oriented north-south, and there's a set of these sensors that are oriented vertically. And each of those has a pair of sensors on them, one on each of those 2 poles, or whatever you want to call them there. One induces or emits an ultrasonic pulse. They're ultrasonic. You can't hear them with your ears. They're too high a frequency for that. And the other one is going to receive the ultrasonic pulse. So you can think of it as like a microphone. So if I just like zoom into this one pair of sensors here, what happens is we're going to use the time it takes for that little pulse of ultrasonic sound to go from the inducer to the receiver. And it's going to be based, that period of time, t, that it took to get from the inducer to the receiver is going to depend on the speed of the wind, the speed of sound in the air, and the distance between the 2 sensors. So if the wind is blowing in the direction from one that goes from the inducer to the receiver, and the pulse is traveling with the wind, it's going to take less time for those sound waves to get from the inducer to the receiver. On the other hand, if the pulse is traveling against the wind, see how I kind of tried to draw it there where the pulse is going upwind? If the pulse is going up the wind, against the wind, it takes more time for the pulse to get to the receiver. In fact, if you had winds that were traveling as fast as the speed of the sound would never get all the way up to the receiver if it was going upwind. In practice, you can't get winds as fast as the speed of sound. There's physical reasons as to how gases work that doesn't happen. But this idea that the time it takes for the pulse of sound to get from the inducer to the receiver, it turns out to depend on the speed of the wind, is a slick trick. Now your book gives you an equation that shows that, but the form they give you is not so useful. I rearranged that equation in a more useful form here to show you that if you want to know the wind speed U, you need to know the distance between the inducer and the receiver, L, the time it took, T, and the speed of sound, C. And that's pretty slick, and you just get the speed of the wind. Turns out, though, that's actually a terrible way to do it, and that is not the way sonic anemometers work. See, that C that's in there is a problem. That C, which is the speed of sound, depends on a lot of nasty things. Not just the temperature of the air, which you probably knew that the speed of sound depends on temperature of the air, but the pressure of the air and like the exact chemical makeup of the air, and also like the extent to which there's like little particles in the air, like dust and soot and smoke and pollen, and oh my gosh, a million things that we don't even measure. So we need a way of doing this so that we don't need to know the speed of sound. And it turns out there's a really slick trick. The math works out really cool. If your instrument is both, if each of those two little sensors on there are both an inducer and a transmitter, a receiver, you can keep alternating the roles of the two on the order of like fractions of a second. So like first the one on the left will emit the sound and the one on the right will receive it, and then you reverse the roles, a half a second later or a quarter second later, and have the one that's on the right be the one emitting the sound and the one that's on the left be the one that is receiving the sound. And if you do the math, okay, we took two different measurements now of the amount of time it took for the sounds to go between the two sensors. One way it's T1 and the other way it was T2. So you have two different measurements of the time. If you actually do the math and plug that into the equation, which now I have crossed out up there, and do all the algebra, you can get that equation that I have there now, with U equals 0.5 times L times, and then keeps going. And you'll see that the value of the speed of sound is canceled out. Isn't that slick? We actually have, by just the engineering of how we did this here and changing, making it so that both of the ends of that sensor are both an emitter and a receiver, we now, an inducer and a receiver, we now have been able to make this work in a way that doesn't require knowing the speed of sound. So in practice, that's how we actually really do it. Now you do that for all three pairs of the sensors on your sonic anemometer, and you get an extremely good measurement of the three-dimensional winds at that location. This is a very slick trick. Maybe not necessarily something you directly need for forecasting wind power or something like that, but maybe as part of a meteorological weather station that is in general about forecasting conditions at the location of your wind farm or something, this could be important. There's other technologies that we can use as an anemometer. Now, your book mentions hot wire anemometers, in part because Landberg, the author of the textbook, has some specific research experience using hot wire anemometers, and if you follow, I think he orients you toward box 19 towards the end of the book as to how he used hot wire anemometers to learn something about the winds on Mars. It's actually kind of an interesting story. Hot wire anemometers are actually not that commonly used in routine meteorological observations and in energy applications and so on. That doesn't tend to be what we use them for. They tend to be on a little probe. See, this is like a hot wire anemometer. I think I found this one on Amazon or something like that. But what you do is, on the end of that probe, there's this little tiny hot wire. And that's where it's going to be measuring the wind. We tend to use hot wire anemometers to measure the wind in like small spaces. Like, the flow through a little gap or a little crack. It's how they measure the rate of air escaping through like a crack in a seal or something like that. It doesn't tend to be meteorological, although it certainly could be. But the way a hot wire anemometer works is actually pretty slick. The hot wire, it uses this very fine wire, and it's an electrical conductor, and it is heated to some temperature above the ambient temperature around it through the flow of electricity. As electricity flows through wires, if they are not perfect conductors, they are heated, and they choose a material here that will heat up. It'll be a hot wire that is then heated by the flow of electricity. But as air flows past the hot wire anemometer, the flow of air over it works to cool the anemometer. So you got two different competing processes here. You know how much you are heating the wire by flowing electricity through it, but you know how much the wire is also cooling by the flow of the wind over it. Well, if you could measure the electrical resistance across the wire, which again, there's standard electronic equipment that does such a thing, you know, components you can buy in the back of Radio Shack and so on. Well, if you can measure the electrical resistance, most materials, the electrical resistance is a function of temperature. So if you know then there's this much electrical resistance on that wire right now, you know the temperature of the wire, you know how much you're heating it, and you know what the temperature is, you know how much heat is getting away, therefore you know how strong the wind is. You are measuring the wind by realizing that the wind is carrying some of this heat away, and that is why the temperature of the wire is what it is, rather than what it would have been if you had just been heating the wire without any flow. This is a really slick trick, and it has very high response rates and so on. But again, it's not really something we very often use in, like, you know, operational meteorology or something like that. It's more of a specialized application, you know, for measuring flow through little gaps and things like that, where you can insert that probe and measure the flow in a way that you could never do with like a cup anemometer or something like that. Now, our final wind speed measuring observation is a Pitot tube. I would draw your attention to the word is pronounced Pitot. Pitot was a French engineer who developed them or whatever. I mean, the reality is Pitot tubes are not very often used to measure winds meteorologically or at a wind, in a wind power application, but they're important for how we calibrate such things, and they have other important applications, as you're going to see. Now, Pitot tubes use a nifty trick to measure the wind speed. They do it by measuring the air pressure. Now, the total pressure, we're going to talk about barometers a little farther down on this list here, but a barometer is an instrument that measures the pressure of the wind. Now, if you just stick a barometer out there, what you are measuring is the total pressure. But that is not of any meteorological value whatsoever. What you actually want, when you look at a map of pressure and you see cyclones and anticyclones the way we did in Module 2, those maps are actually of a quantity called static pressure. Static pressure is the pressure of the location caused by, you know, the force of little molecules bouncing against the surface, the kinds of things you learn in like high school physics class or ATS 113 or something like that. That's what we want. That is the pressure. Well, that is what meteorologists want. When they want to like make a map of pressure and they want to draw contours of pressure, the isobars, they want static pressure. That is something that a barometer can give us if it is sheltered from the wind. But what the barometer really gives you is total pressure. Total pressure is the sum of that static pressure, which is the meteorologically interesting part, and dynamic pressure. Dynamic pressure is the pressure created by the wind, the force of the wind hitting your barometer. When a big strong wind blows on a building and knocks it over, it's because it is exerting a pressure on every square meter of the wall of the building, and the dynamic pressure exceeded the design of the wall. The force of the wind itself hitting an object, that is dynamic pressure. And a barometer can't tell the difference, which is why to measure the static pressure we have to measure with our barometers indoors. Okay? But Pitot tubes take advantage of the fact that it doesn't have to be that way. You could deliberately take the pressure, measure the pressure in the wind and get the total pressure, and you could deliberately take the pressure away from the wind and get the static pressure, and from that you could subtract and get the dynamic pressure. Okay? I mean, that's just arithmetic, right? Use two barometers to measure the difference between the static pressure, the static pressure and the total pressure. Take the difference, you get the dynamic pressure. And dynamic pressure is very closely related to wind speed through this very simple equation here. You can solve for u, no problem. It's just 1/2 times rho, the density, times u squared. Pretty straightforward. In practice, actually, they're even simpler than that. But I couldn't find any diagrams of Pitot tubes that didn't get into way too much detail as to how it's actually done. But Pitot tubes then are a slick way of doing this. Just measure pressure in the wind, that's total pressure. Measure pressure out of the wind, that's static pressure. Take the difference, you get dynamic pressure. From dynamic pressure, it's just math to get to wind speed. Pitot tubes are how we actually calibrate and control the wind speed in a wind tunnel, where you can have enormously precise measurements of exactly what the wind speed is, and you can control it in a very good way. But there's actually even a better application and a more important application of Pitot tubes. Pitot tubes are how aircraft determine their airspeed. If you look under the wing of an aircraft, you often see this sort of thing. It looks a little bit like a pipe sticking out the bottom of the wing, or like on this jet aircraft here I circled, there's a little pitot tube sticking out the side. There are a number of like little things on the underside of wings of aircraft or on the underside of the body. Some of them are like types of antennas and so on. But the ones that stick out like this are pitot tubes. And they are measuring the speed of the air flowing over the aircraft. And they'll be then sheltered inside of the tube. There's a second instrument measuring the the pressure sheltered from the wind. And from the difference, they're figuring out the speed of the flow, which is really just the airspeed of the aircraft. Now, in a modern aircraft, that's usually checked against GPS and stuff like that too. But this is how airspeed has been computed for 100 years of aviation history. Pretty slick. Not typically used directly in observational, practical meteorology. Not very often are they actually used like at a wind farm, but they are how those kind of instruments were calibrated in wind tunnels and so on. Pretty slick. Now, since we've been talking about all these anemometers and so on, with the exception of the sonic anemometer, which could measure wind direction, the rest of them could only measure wind speed. On the other hand, there's not really all that hard to measure the wind direction. We're going to use a wind vane to do it. Now, here I have two views of a wind vane, and they're lined up the way they should be there. You can kind of see from the bolts on this top view and the bolts you can see on the side view. This is just the two, I just tipped it over there like this. Again, this came from like a patent application or something that I had found online. Just to give you a sense, you can follow that link and go see it yourself. Anyway, what I wanted you to draw your attention to is how wind vanes actually work. See, they're put out there in some flow that originally they're not necessarily pointing directly upwind in. See how this flow is not exactly parallel to the orientation of the wind vane? But by doing that, by having that one big tail on the back end of the wind vane, there'll be more force by that wind exerted on that tail than up there on the pointy front end. And that will exert a force on the tail to turn this to be upwind. And see how the wind vane will shift until now it has reached a stable solution where the force is equal on the two sides of the big fat tail of the wind vane. And so the wind vane will keep pointing upwind. Now the wind vane itself is of course just mounted on a shaft, and the shaft turns. The shaft itself is not like attached to some generator or something like that. That wouldn't really work. Rather, it's attached to a piece of electronics called a potentiometer. A potentiometer is just a little dial that controls like voltage on a line. It's the same way like the volume knob on an old radio or an old television worked or something like that. It's just a little knob that turns and it regulates the voltage on a line. And so it's pretty straightforward then to measure the changes in the voltage, and you know what direction the knob is turned and therefore what direction the wind vane is pointing. And then that gets converted to a wind direction, of course, by the data logger itself. Your book goes into some kind of interesting detail about the fact that there are dead zones on a wind vane where there are little ranges, usually just a little 5-degree range where it can't measure the wind because of how potentiometers work. Potentiometers don't exactly turn all the way around the way a wind vane can. But we're not going to get bogged down in that. I don't want to get into the engineering of how they get around that. Wind vanes are surprisingly accurate little weather instruments. They're certainly accurate to within just a few degrees. In fact, really, the main limitation as to how good of information you can get from a wind vane is how accurately you sighted it. When you put a wind vane in, it's extremely important that it be, that the electronic works of the wind vane know which way is north. Okay, because that will, if you mounted the wind vane crooked, it will point, the wind vane will point upwind. It'll just be not correct as to what direction that is. Okay, it'll think, oh, that's north, but no, that way's north, not that way. So you have to be extremely careful with that, and in fact, correctly sighting a wind vane so that orienting it correctly to the north with respect to true north is in fact quite a challenge. As your book discusses, it is actually surprisingly difficult at just a location out in the field to figure out which way is north to the kind of precision we need here. I mean, we need to know which way is north. Not like, that's kind of parallel to that road over there. No, I mean, we need to know it to like a fraction of a degree, and that is a surprisingly difficult thing to do, but we're not in a surveying class here or something like that. We don't need to worry about those details. Other people do that. All right, before we move on to part 3 of this lecture, let's stop and ask a couple quick questions here. Question 4. When determining the speed based on the rate of rotation of a cup anemometer, We assume that the wind resistance of the cups moving upwind is 0. Is that true or false? Alright, make a choice for those two options and get a little feedback before you move on to question 5.